Welcome to Everything About Robotics Explained.
Imagine a robot needing to gently pick up a fragile egg or safely interact with a human hand, distinguishing a light touch from a firm grasp. How does it sense these subtle differences in pressure and contact force? Capacitive force sensing works by measuring changes in electrical capacitance that occur when a sensor deforms under mechanical force. It is a highly sensitive method for detecting pressure, touch, and even proximity, allowing robots to perceive their physical environment with great accuracy. At its core, capacitive sensing relies on the fundamental principle of a capacitor. A capacitor is essentially two conductive plates separated by an insulating material called a dielectric. The capacitance, which is the ability to store an electrical charge, is directly proportional to the area of the plates and the permittivity of the dielectric material, and inversely proportional to the distance between the plates. When a force is applied to a capacitive force sensor, it causes a physical deformation. This deformation can manifest in several ways. The most common is a change in the distance between the conductive plates as the dielectric material compresses. Alternatively, the overlapping area between the plates might change, or the properties of the dielectric material itself, like its permittivity, could be altered under pressure. Each of these physical changes directly influences the overall capacitance of the sensor. To achieve this, many capacitive force sensors are constructed using flexible and compressible dielectric materials, such as silicone or specialized elastomers, sandwiched between conductive electrode patterns. When external pressure is applied, the dielectric material compresses, reducing the separation between the electrodes and thereby increasing the measured capacitance. This change in capacitance is then converted into an electrical signal that a robot's control system can interpret as a quantifiable force. Implementing capacitive force sensing into robotic applications involves careful consideration of sensor design and integration. Designers must choose appropriate materials and electrode geometries to match the desired sensitivity and dynamic range for specific tasks. For example, a sensor for fine manipulation requires much higher sensitivity than one designed for collision detection. Calibration is also a critical step, ensuring accurate and repeatable force measurements across the sensor's operational range. These sensors are incredibly versatile, finding applications in robotic grippers for delicate object handling, tactile skins for human-robot interaction, and even as soft contact sensors for robot navigation and collision avoidance. Their ability to provide distributed and continuous force feedback allows robots to perform tasks that requiring fine motor control and intelligent physical interaction with their surroundings. One significant advantage of capacitive force sensors is their inherent robustness and low power consumption, making them ideal for battery-operated robotic systems and long-term deployment. They can also be manufactured to be highly flexible and conformable, allowing them to be integrated seamlessly onto curved or irregular robotic surfaces. This offers a distinct benefit over more rigid sensing technologies, broadening the possibilities for tactile feedback in complex robotic designs. Ultimately, understanding how capacitive force sensing works provides a crucial insight into how robots achieve a more nuanced and responsive interaction with the world. By translating physical pressure into measurable electrical signals through changes in capacitance, these sensors empower robots with a sense of touch that is vital for advanced manipulation, safe collaboration with humans, and intelligent adaptation to unstructured environments, moving us closer to truly versatile and intuitive robotic systems.
If you love robotics, like, subscribe, and keep building with us.